Welcome to the Deep Dive. And a special welcome today, this one's specifically for the students and followers of Mr. Chi.
That's right. We've got your grade 9 natural sciences pre-examination material right here.
Yep, the full 60 marks covering terms 3 and 4, that's energy and change and earth and beyond.
Yeah.
If you're, grinding through this prep, think of this as your express lane.
Exactly. We're not just giving you an answer key. No. Our mission today is to really break down every single part question. We want you to get why the answer is correct.
So whether you're feeling a bit shaky on the basics or you're aiming for those top marks, we're diving deep enough for everyone.
We'll cover the science, the concepts, the mechanisms behind it all. We're connecting the dots for you.
From static shocks and calculating circuit current, all the way to how rocks are formed and what's happening way out in space.
It's a strategic breakdown, not just a quick look.
Okay, but before we jump into the first section, Section A, just a quick heads up.
Oh, yeah. Important bit. If you find this detailed approach helpful, and we really hope you do, please share this deep dive.
Tell your friends, your study buddies, like the content, subscribe to the channel if you haven't already.
And definitely follow Mr. Chi everywhere, Instagram, TikTok, Facebook, YouTube. Seriously, it helps keep resources like this coming your way. It's your shortcut, really.
Couldn't agree more. Okay, structure for today. We're hitting Section A, energy and change, first. That's the big one, 60% of the marks. Then we'll move to Section B, earth and beyond.
Let's do it. Section A it is.
Right. Starting with question 1, multiple choice. First up, Q1.1 asks you to pick out a non-contact force. The options are tension, normal force, friction, and electrostatic force.
Okay, this is fundamental classification, isn't it?
Yeah.
You've got contact forces, things that need to touch.
Like pulling a rope for tension or pushing something for normal force.
Or rubbing surfaces for friction.
Yep.
They all require physical contact. So the odd one out, the non-contact force here, has to be D, electrostatic force.
And that acts over a distance, right? Like magnetism and gravity.
Exactly. No
Okay.
touching required. Okay, Q1.2 then builds on that. If you increase the distance between two charged objects, what happens to the electrostatic force between them?
The options are usually increase, decrease, stay the same.
And the answer is B, it decreases. But hang on, let's push this a bit further for those aiming high. It doesn't just decrease linearly.
You mean that inverse square law thing?
Precisely. It follows an inverse square relationship with distance. So what does that actually mean?
Well, if you double the distance, the force doesn't just get cut in half, does it?
Nope. It drops to 1/4 of its original strength. Double the distance, force divided by 4. Triple the distance.
Force drops to 1/9.
You got it. 1/3 squared. It weakens really fast with distance. That's why, static electricity is noticeable when things are close, like a balloon on your hair, but pretty much undetectable, even a short distance away.
Okay, that rapid drop-off is key context. Cool. Moving on to Q1.3 about magnetic fields. Specifically, the field lines outside a bar magnet. Where do they go?
The rule, the convention we use, is that the field lines emerge from the North Pole and curve around to enter the South Pole. So that's option B.
North to south, outside the magnet.
Right. Inside, they actually run south to north to complete the loop. But the standard visualization focuses on the external field, N to S.
Okay, good clarification. Now, stepping away from multiple choice, question 2.1 is super basic but crucial. Define force. 2 marks.
Keep it simple. Really simple. A force is just a push or a pull. That's it. 2 words, basically. Push or pull gets you the marks.
Perfect. Okay, Q2.2, the classic scenario. Rubbing a ruler with a cloth, then picking up tiny bits of paper. Q2.2.1 asks how the ruler gets positively charged.
Right. This is charging by friction. It all comes down to electrons. When you rub the ruler and the cloth together, some materials hold on to their electrons more tightly than others.
So one material wins the electrons.
Kind of. In this case, the cloth wins. It pulls electrons off the ruler. Electrons are negative. So the ruler loses negative charges.
And if it loses negatives, it's left with more positives.
Exactly. It already had positive charges, the protons in its atoms, but they were balanced by the electrons. Now, with fewer electrons, the positive charge dominates overall. The ruler becomes positively charged.
Crucially, only electrons move, right? Protons are stuck in the nucleus.
Absolutely critical point. Protons never move in these standard electrostatic processes. Only the light mobile electrons get transferred.
Okay, got it. Then Q2.2.2. Why does this positively charged ruler attract neutral pieces of paper? The paper doesn't have an overall charge.
This is where it gets interesting. It's about polarization, or inducing a charge separation. The paper is neutral overall, yes, meaning it has equal amounts of positive and negative charge all mixed up.
So what happens when the positive ruler comes near?
The positive ruler pulls on the negative charges, electrons, within the paper molecules. So the electrons in the paper shift slightly, moving a tiny bit closer to the ruler side of the paper bits.
And the positive charges in the paper?
They get pushed away, repelled by the positive ruler, so they shift slightly towards the other side of the paper bits.
So within each neutral piece of paper, you get a temporary separation, negative side closer to the ruler, positive side further away.
Exactly. That's induced polarization. Now think about the forces. The positive ruler attracts the closer negative side of the paper and repels the slightly more distant positive side.
And because the negative side is closer, the attraction is stronger.
Just slightly stronger. Remember that inverse square law. Distance matters. Even that tiny difference in distance means the attractive force wins out over the repulsive force. And that's why the neutral paper jumps up and sticks to the charge ruler. It's a temporary induced attraction.
Wow. Okay. That makes sense. It's subtle but powerful. All right. Q2.3, safety during a thunderstorm. We need 2 precautions.
Lightning, massive static discharge, basically. You want to avoid being the easiest path for it to take to the ground. So, rule 1, stay away from tall, isolated objects.
Like a lone tree in a field.
Exactly. Lightning tends to strike the highest point. Rule 2, get indoors if you can. Stay away from windows and don't use corded phones or electrical appliances plugged into the wall.
What about being in a car? Is that safe?
Surprisingly, yes, very safe. But it's not because the rubber tire is insulating you. That's a myth.
Oh. So why is a car safe then?
It's the metal body that acts as a Faraday cage. If lightning hits the car, the electrical charge flows around the outside of the metal shell and harmlessly into the ground.
So the electricity stays on the outside, protecting the inside.
Precisely. As long as you're not touching the metal parts of the frame inside, you're shielded.
Okay, let's shift gears now. Moving from static charge to charges in motion, electric current, and circuits. Back to multiple choice briefly. Q1.4 revisits charging. A glass rod gets positively charged when rubbed with silk. What happened?
We've nailed this one already, haven't we? If it's positive, it must have lost negative charges. So D, electrons were removed from the rod. Again, protons don't move.
Good reinforcement. Q1.5 asks about the device that converts chemical energy into electrical energy.
That's the job of the cell or battery, option D. It's the chemical reaction inside that provides the push for the electrons.
Which leads us perfectly into Q3.1.2, defining the function of that battery or cell in a circuit. What's its purpose?
Its job is basically to provide the energy. It creates a potential difference, we might call it voltage, across the circuit. And it's this potential difference that forces the electrons, the current, to flow around the circuit.
So it's the energy source driving the electron movement.
Exactly. Without it, the flow would stop almost instantly because of resistance in the wires and components.
Okay, now Q3.2 looks at an investigation. There's a table showing how changing the length of a conductor affects the current. As length goes up from 3 centimeters to 15 centimeters, the current drops from 5 amps down to 1 amp.
A clear trend there.
Right. So Q3.2.1 asks you to state the hypothesis based on this data.
The hypothesis needs to link the two variables directly based on what the table shows. Something like, when the length of the conductor increases, the current strength decreases.
A clear inverse relationship.
Yep. And for the 2 marks, you need to state that relationship clearly.
But why does a longer wire reduce the current? Let's dig into that.
Think of the wire as a pathway for the electrons. The electrons don't just flow freely, they bump into the atoms that make up the wire. This bumping is resistance.
Like friction for electrons.
Sort of, yeah. Now, if you make the wire longer, the electrons have to travel further through this bumpy material.
So they have more chances to collide with atoms along the way.
Exactly. More collisions mean more opposition to their flow. So a longer wire naturally has a higher resistance.
And Ohm's law tells us if resistance goes up and the voltage from the battery stays the same, the current must go down.
Precisely. V is constant, and R increases, I has a decrease. It all links together. Longer wire, more resistance, less current.
Makes sense. Okay, finishing up this experiment section, Q3.3.1 and 3.2 ask for the variables. What was deliberately changed and what was measured?
The thing the experimenter controls and changes is the independent variable. In this case, that was the length of the conductor.
And the thing they measure to see the effect of that change.
That's the dependent variable. Here, it was the current strength, measured probably using an ammeter.
And other things, like the wire's thickness or material or the battery voltage, should be kept the same, right?
Absolutely. Those are the controlled variables. You need to keep them constant to be sure that only the length is causing the change in current you're observing. It's about a fair test.
Right, back to some quick multiple choice questions on circuit components and safety. Q1.6 shows a diagram of a standard 3-pin plug and asks you to identify the earth wire.
Yeah, you need to recognize this. The earth wire is usually connected to the longest pin, often at the top. In diagrams, it might be labeled X or A, or sometimes shown with green and yellow stripes.
And its job is purely safety, isn't it?
Entirely. If something goes wrong inside an appliance with a metal casing, say, the live wire touches the casing. The earth wire provides a safe path for that dangerous current to flow directly to the ground.
Which causes a large current.
A very large current, yeah, which immediately blows the fuse or trips the circuit breaker, cutting off the power and preventing you from getting a nasty shock if you touch the appliance. It's vital.
Okay. Q1.7 gives a sequence of components: connectors, resistors, fuse, circuit breaker. Is that the right order or classification?
Well, option C lists those. Connectors join things, resistors impede current flow, and fuses and circuit breakers are both safety devices that interrupt the circuit if the current gets too high.
What's the main difference between a fuse and a circuit breaker again?
A fuse contains a thin wire designed to melt and break the circuit permanently if the current exceeds a certain level. You have to replace it. A circuit breaker is an automatic switch that trips open but can be reset and reused. Much more convenient and standard in modern homes.
Got it. And Q1.8 asks about current in a parallel circuit. What's the key rule?
The defining characteristic is B. The current divides among the branches. The total current leaves the battery, reaches a junction, and then splits up, with some current going down each available path.
Unlike a series circuit where the current is the same all the way around?
Exactly. This splitting is fundamental to how parallel circuits work.
Okay, that leads us perfectly into question 4, which is all about comparing parallel circuits. We have circuit 1 with fewer bulbs in parallel and circuit 2 with more bulbs in parallel. Q4.1 asks why the voltmeter readings across all the bulbs in either circuit are the same.
This goes back to the definition of parallel connection. When components are wired in parallel, each one is connected directly across the positive and negative terminals of the power source.
So each branch gets the full battery voltage.
That's right. Voltage is the potential difference between 2 points. Since every parallel branch connects to the same 2 points, the battery terminals, they all experience the same voltage. Parallel circuits are voltage constant. They divide the current, not the voltage.
Okay. Now Q4.2. This is often a tricky concept. Circuit 2 has more bulbs in parallel than circuit 1. The question notes that the total current coming from the battery is higher in circuit 2. Why? It feels like more bulbs should mean more resistance.
Yeah, this trips people up.
Yes.
But think about it like roads again. Adding another bulb in parallel is like adding another lane to a highway.
Okay.
Does adding an extra lane make it harder for traffic to flow overall?
No, it makes it easier. More cars can get through in total.
Exactly. Adding another parallel path doesn't increase the resistance of the existing paths. It just provides more paths for the current to flow simultaneously.
So more pathways means the overall opposition, the total resistance of the circuit, actually goes down.
Precisely. It's easier for the battery to push current through the whole system because there are more routes available. Lower total resistance means, by Ohm's law, VIR, a higher total current flows from the battery.
That makes sense when you think about it that way. More branches, less overall resistance, more total current.
Got it.
Okay, Q4.3 is a calculation. In circuit 2, the total current from the battery is 3 amps. It splits between 3 identical bulbs connected via ammeters A4, A5, and A6. What does each ammeter read?
If the bulbs, and therefore the branches, are identical, they have the same resistance. This means the total current will split equally among them.
So 3 amps total divided by 3 branches.
Each branch gets 1 amp. So A4 reads 1A, A5 reads 1A, and A6 reads 1A. Simple division as long as the branches are identical.
Right. And Q4.4 asks about the brightness of the bulbs in circuit 2. How do they compare?
Well, we know they're identical bulbs.
Hmm?
And we know from Q4.1 that they all get the same voltage because they're in parallel.
And from Q4.3, they also get the same current, 1A each.
Right. Brightness depends on power. Power equals voltage x current. Since both V and I are the same for each bulb, their power output and therefore their brightness will be exactly the same, all equally bright.
Okay. Finally, Q4.5 asks us to summarize the key difference and potential difference voltage distribution between series and parallel circuits. Let's tabulate this clearly.
Good idea. In a series circuit, the total voltage from the battery is shared or divided among the components. So the sum of the voltages across each component equals the total battery voltage. Think of IV total V1 plus V2 plus V3 dots.
Okay, voltage adds up in series. What about parallel?
In a parallel circuit, the voltage is the same across every component or branch.
Yeah.
Each one gets the full battery voltage. Think V total V1 equals V2 equals V3 dots.
So series divides voltage, parallel divides current, but keeps voltage the same.
That's the essential difference, yes. Crucial for understanding circuit behavior.
All right, let's zoom out now to the big picture, generating electricity. Question 5 focuses on a nuclear power station. Q5.1 asks us to put 4 steps in the correct order. The steps involve steam, turbines, generators, and heat release.
Okay, the goal is always to turn some form of energy into rotating mechanical energy, which then turns a generator. So you need heat first.
Right, step D says heat is released through nuclear fission. And we should note the correction here. The original paper might have mistakenly said fusion, but it's fission in power plants on Earth.
Absolutely, critical distinction. So D is first. Nuclear fission releases immense heat. What does that heat do?
It boils water, right? So step B, steam is produced.
Yep, high-pressure steam. What does steam do in a power plant?
It pushes things. It turns the turbine step A.
Right, the steam blasts against the turbine blades, making them spin. And finally,
the spinning turbine is connected to the generator, which then produces electricity. So step C, rotation of turbines, drives the generators.
so the sequence is DBAC. Fission, heat, steam, turbine spins, generator makes electricity. Got it. DBAC. Then Q5.2 asks, which of these steps is unique to a nuclear plant and doesn't happen in a coal-fired power station?
Well, coal plants also use heat to make steam to turn turbines to drive generators. The BAC steps are basically the same.
So the unique part must be how the heat is generated.
Exactly. Step D, heat released through nuclear fission. Coal plants release heat by burning coal, a chemical reaction, not nuclear. So D is the answer.
Makes sense. Q5.3 asks for 2 advantages of using nuclear energy.
There are some significant ones. First, during operation, nuclear plants don't burn anything, so they don't release greenhouse gases like 2O2, or other air pollutants like sulfur dioxide that cause acid rain. So it's considered a clean energy source in terms of air pollution and climate change.
Okay, that's a big one. What's another? Reliability and efficiency. A very small amount of nuclear fuel, like uranium, contains a huge amount of energy. This means plants can run for a very long time, like a year or more, without refueling, providing a consistent, reliable baseload power supply 247. And once the plant is built, the fuel costs are relatively low compared to constantly buying coal or gas.
So clean operation and efficient, reliable power generation.
Those are the key selling points, yes. Though waste disposal and safety are, of course, major considerations on the other side.
Right. Okay, let's tackle the final question in this section, Q6. It's a cost calculation for running a washing machine. The details. Power is 480 watts. It runs for 1.5 hours. And electricity costs are 1.65 per kilowatt hours. Q6.1 is the first essential step.
Yes, look at the cost unit. Rands per kilowatt hour. But the power is given in watts. You must convert.
How we convert watts to kilowatts?
Divide by 1,000. Kilo means 1,000. So 480 watts divided by 1,000 gives you 0.48 kilowatts. Kilowatt. Always do this first if the units don't match.
Okay, 0.48 kilowatts. Now Q6.2, the actual calculation using the formula. Cost, power kW, 8 time hours, A unit price, RKWH.
Exactly. Just plug in the numbers we have. Cost equal 0.48 kilowatts, 1.5 hours, A are 1.65 kilowatts.
Let's break that down. First, maybe multiply the power in time. 0.48 kilowatt times 1.5 hours.
That gives you 0.72. And notice the units. Kilowatts times hours gives kilowatt hour, so 0.72 kilowatt hours. This tells you the total amount of energy the washing machine used.
Right, the kilowatt hour is a unit of energy, not power.
Correct. Now you just multiply that energy amount by the cost per unit of energy.
So 0.72 kilowatt hour times R 1.65 per kilowatt hour.
Pull out the calculator, gives you R1.188.
And we usually round money to 2 decimal places, so R1.19.
R1.1, that sounds right. Make sure you show your steps, the conversion, plugging into the formula, and the final answer with the rand sign.
Okay, we've covered energy and change. Let's shift focus now to section B, Earth and beyond. This is worth 40% of the marks.
Right, moving from circuits and forces to planets and rocks.
Question 7 starts with a diagram showing Earth's spheres. Q7.1 asks to identify sphere D, which represents all the water on Earth.
That's the hydrosphere. Hydro means water. It includes oceans, lakes, rivers, groundwater, ice caps, glaciers, and even water vapor in the air.
We should probably quickly name the others usually shown. Geosphere or lithosphere is the rockland.
Biosphere is all living things, plants, and animals.
And atmosphere is the layer of gases surrounding the Earth.
Got them all. Okay, Q7.2 asks for an explanation of an interaction between the biosphere, labeled B, showing maybe plants' life, and the hydrosphere, labeled C, maybe water.
How do living things and water interact?
A very fundamental interaction is needed for life itself. Plants, biosphere, absorb water, hydrosphere, through their roots. They need this water for photosynthesis, to transport nutrients, and just generally to survive and grow.
So biosphere takes water from the hydrosphere for life processes. That seems like a solid 2-mark answer.
Absolutely. You could also mention animals drinking water or transpiration, where plants release water vapor back into the atmosphere, linking to a third sphere. But simple absorption is key.
Okay, moving to Q8, which shows a flow chart of the rock cycle. Q8.1 asks to identify rock type B. The chart shows it forming from other rock types under heat and pressure.
Heat and pressure transforming existing rocks. That screams metamorphic rock. Meta means change. Morphic means form. Changed form.
So B is metamorphic rock. Right. Q8.2 asked us to explain what's happening during specific numbered processes on the chart. Let's take process 2, which goes from metamorphic rock to magma.
If metamorphic rock, which is solid, turns into magma, which is molten rock, what must have happened?
It must have melted. So process 2 is melting. Extreme heat deep within the earth melts the rock.
Perfect. Now process 3 goes from magma to igneous rock.
Magma is molten. Igneous rock is solid rock formed from molten material. So process 3 must be the opposite of melting. It's cooling or solidification.
Exactly. Magma cools down either slowly underground or quickly if it erupts as lava and crystallizes into igneous rock.
Okay. And process 4 goes from igneous rock to sediment.
Right. You've got solid igneous rock exposed on the surface. How does it turn into sediment, which is like little bits, sand, or pebbles?
Things have to break it down, don't they? Like wind and rain.
That's weathering, the physical breakdown, like ice wedging, or chemical breakdown, like acid rain, of the rock. And then erosion is the transport of those broken bits by wind, water, or ice. So process 4 is weathering and erosion, leading to sediment formation.
Weathering breaks it, erosion takes it away. Got it. Finally, Q8.3 asks for one example of an igneous rock and one of a sedimentary rock.
Okay, igneous formed from cooled magma or lava. Think common ones. Granite is a classic intrusive example.
Or basalt, the dark rock from volcanoes.
Right.
Or maybe pumice, the one that floats.
Any of those are perfect examples. Granite, basalt, pumice. Now, sedimentary rock formed from layers of compressed sediment.
Like sandstone, made from sand grains cemented together.
Sandstone is a great one. Or limestone, often formed from shells and skeletons. Or shale, made from compressed mud or clay. Any of those work.
All right, let's move on to Q9, which deals with mining and specifically extracting iron in a blast furnace. Q9.1 asks about the name. Why is it called a blast furnace?
The name is quite literal. To get the incredibly high temperatures needed to melt iron ore and allow the chemical reactions to happen, they blast huge quantities of hot air into the bottom part of the furnace.
So it's named after the blast of hot air.
Exactly. Through pipes called tuyères. This provides the oxygen needed for the coke, a form of carbon fuel, to burn intensely. Without the blast, it wouldn't get nearly hot enough.
Okay. Q9.2 asks for 2 negative environmental impacts of extracting iron this way.
Yeah, this process isn't exactly eco-friendly. A major one is the release of carbon dioxide, CO2. Burning the coke releases CO2, and the limestone added to remove impurities also decomposes, releasing more CO2.
And CO2 is a greenhouse gas contributing to climate change.
Right, that's impact number 1. Impact number 2 relates to the fuel source. The coke is made from coal.
And coal is a fossil fuel, non-renewable.
Exactly. So iron production relies heavily on mining and consuming a finite fossil fuel resource, often through environmentally disruptive methods like strip mining. Plus, burning coal derivatives releases other pollutants too.
So greenhouse gas emissions and reliance on non-renewable fossil fuels. Got it. Q9.3 is quick. Which Earth sphere do we get valuable minerals like iron ore from?
We mine rocks and minerals from the solid Earth, so that's the lithosphere or geosphere.
Straightforward. And Q9.4 asks how steel is made, given that the iron from the blast furnace isn't usually used as is.
Pure iron is actually quite soft. To make it strong and useful, we turn it into steel, which is an alloy mixture of metals, or a metal and a nonmetal. Steel is mostly iron mixed with a small, carefully controlled amount of carbon.
How is that done?
Typically, they take the molten iron from the blast furnace and mix in the carbon, sometimes removing excess carbon first, often in another process, like using a basic oxygen furnace. The precise amount of carbon determines the properties of the steel, making it harder, stronger, more versatile. Okay, final stretch. We're looking up now. Q10 is about the layers of the atmosphere, using a graph showing temperature versus altitude. Q10.1 asks us to name layers A and C. Layer A is the lowest one.
That's where we live, where weather happens. That's the troposphere.
Correct. And layer C is above layer B. The temperature drops significantly in layer C.
After the stratosphere B, where it gets warmer, the next layer up where it gets colder again is the mesosphere. Meso means middle.
Troposphere, stratosphere, mesosphere. Got it. Q10.2 wants us to read the temperature from the graph for layer B, stratosphere, at an altitude of 20 kilometers.
Okay, find 20 kilometers on the height axis, go up to the line for layer B, then read across to the temperature axis. Looks like it's about negative 60 degrees Celsius.
Minus 60 C. Sounds about right from typical atmospheric profiles. Okay, Q10.3 asks if the temperature trend in layer B, the stratosphere, as you go higher, specifically from 20 kilometers to 50 kilometers.
Looking at the graph for B, between 20 and 50 kilometers, the line goes up towards the right. So as the height increases, the temperature also increases. It goes from negative 60 C up to around 0 C at 50 kilometers.
This is unusual, isn't it? Temperature increasing with height. It's called a temperature inversion. Why does this happen specifically in the stratosphere?
This links to Q10.4, doesn't it? It asks for the name of the gas layer found in layer B that protects us from harmful UV radiation.
Precisely. That gas is ozone, O33. The stratosphere contains the ozone layer.
And ozone absorbs UV light.
Yes, it's very good at absorbing harmful high-energy UV radiation from the sun. When the ozone molecules absorb this energy, they heat up.
So the absorption of UV by ozone heats the stratosphere.
Exactly. And since most of the absorption happens higher up in the stratosphere where the UV is strongest, the top of the layer around 50 kilometers gets heated the most, causing the temperature to increase with altitude throughout that layer. It's a direct consequence of the ozone layer doing its job.
Cool. Okay, last question. Q11 takes us beyond Earth's atmosphere to stars. Q11.1 asks for a definition of nuclear fusion. We contrasted this with fission earlier.
Right. Fusion is the process that powers stars. It's where light atomic nuclei, primarily hydrogen, are slammed together under incredibly intense heat and pressure.
Like in the core of the sun.
Exactly. They fuse or combine to form heavier nuclei like helium. And the key thing is, this process releases a tremendous amount of energy, way more than fission, per mass. Light elements for heavier elements plus massive energy release.
Okay. And finally, Q11.2 about black holes. Why can't light escape from a black hole?
It comes down to gravity. A black hole is formed when a massive amount of matter collapses into an incredibly tiny space, creating a gravitational field that is unimaginably strong.
Stronger than anything else.
So strong that the escape velocity, the speed needed to break free from its gravitational pull, is greater than the speed of light.
And since nothing can travel faster than light,
not even light itself can escape once it crosses a certain boundary, called the event horizon. It's trapped by the extreme gravity. Light goes in, but it can't come out. That's why they're black.
And that brings us to the end of the 60 marks. Wow, we covered a lot there, from, electron behavior in circuits right up to the life cycle of stars and rocks.
We really did. And the main goal, just to reiterate for everyone listening, especially Mr. Cheese students, wasn't just ticking off answers. It was about understanding the why.
Yeah, seeing the connections, like how conductor length links to resistance and current.
Or how adding parallel paths actually lowers total resistance, even though it seems counterintuitive at first. Or understanding why the stratosphere gets hotter with height. It's that deeper understanding the mechanism that separates okay scores from really great ones.
Absolutely. Knowing DBAC for the power plant is one thing. Understanding fission, steam, turbines, and generators is another.
And we touched on both nuclear fission used in power plants, which we can control, and nuclear fusion, which powers stars naturally.
Which leads nicely into our final thought for you to ponder.
Yes, a little something to chew on after the exam, maybe. We control fission on Earth. Fusion happens in stars under extreme conditions. What's the fundamental difference in the conditions needed to think temperature and pressure that makes controlling fusion power here on Earth so incredibly difficult compared to fission, even though we know fusion releases even more energy?
Ooh, that's a good one. What makes containing a star on Earth so hard? Definitely something to think about.
So for all of Mr. Cheese students and followers tuning in, use this deep dive. Treat it like your personal study guide. Rewind, replay the bits you found tricky.
Yeah, whether it's the cost calculation or the Faraday cage or the rock cycle processes, go back and solidify your understanding.
And please, if this was helpful, do us and Mr. Chi a favor. Share it. Let your classmates know. Hit that like button, subscribe to the channel for more content like this.
And don't forget to follow Mr. Chi on all his platforms: Instagram, TikTok, Facebook, YouTube. Stay connected, stay informed.
We wish you the absolute best of luck with your pre-examination preparation. You've got this.
You really do. Go ace that exam. And we'll catch you on the next deep dive.